We're going 4 times further than the moon. We are not serviceable. We have to work when we get out there.
Hey everyone, this is our last episode of Season 3 of The Art of Manufacturing. Don't worry, more content isn't far behind. In fact, we're planning a couple cool surprises in a few months, and I can't share much, but stay tuned. In the meantime, make sure to subscribe to the podcast on your favorite player and sign up for our mailing list at makeitinla.org/connect so you'll never miss an episode. And please spread the word to your friends and colleagues so we can grow our fan base and build more partnerships to bring you more great content. Thanks.
Are you ready? All right, let's go.
Manufacturing is sexy. Sounds crazy? Just wait. I'm Z Holly, host of The Art of Manufacturing. Your behind-the-scenes look at how people who make stuff are trying to make it in their industries. If you've ever wondered how to build a brand, a business, or just a better mousetrap, tune in and enjoy. This week's guest is building a time machine, and I'm totally serious. Well, sort of. The James Webb Space Telescope will let us look billions of years back in time. With a projected cost of $9 billion, it's the most complicated science project NASA's ever launched. When you think of manufacturing, you probably imagine mass production, but the Webb is one of a kind. And because it's headed 1 million miles away into orbit past the moon, if something breaks, it can't be fixed. Have you ever been in charge of a project that was too big to fail? Well, the buck stops with Scott Willoughby, the director of the program, and he has one shot at getting it right. I was curious, how can you take risks and innovate when you're working on something so high stakes and under such big scrutiny? So I went to Northrop Grumman and Segundo to find out. We start with a special behind-the-scenes tour of the telescope from systems engineer Krystal Puga. And then Scott joins us as we talk about the risks and rewards and what's next for the program. And we also hear about Scott and Krystal's backgrounds, and I suspect you'll be surprised. We hear about that and a whole lot more on this week's episode of The Art of Manufacturing.
James Webb is first and foremost a space observatory. So its mission is to try to look back in time 13.4 billion years in the past to observe the very first light. And as part of that, since we're looking so far back in time, it gives us an opportunity to also try to learn about the assembly of galaxies, the birthplace of stars, and we even have instrumentation on board that will allow us to look into planets to see if they have the compositions for life.
What is special about this telescope?
Oh man, I think everything is special about this telescope.
Okay, but what is it? Like this, we have the Hubble. Why isn't the Hubble good enough?
One of the key differences, Hubble has one mirror that's about 2.4 meters across, versus James Webb has a mirror that's 6.6 meters across. So the larger the collecting area, or the larger the mirror, that allows us to have more sensitivity so that we can see that light that's coming from so far away.
Where is this going to be?
So another really great difference between the Hubble and the James Webb. Hubble is actually in low Earth orbit. It's about 350 miles, from the Earth's surface, versus the James Webb is actually going to be about 1 million miles away from Earth at the second Lagrange point, which is on the opposite side of the moon.
So tell us what a Lagrange point is.
A Lagrange point is essentially a state between two bodies where you're at a gravitational equilibrium.
And so is it special because it allows the telescope to stay in one place?
So the second Lagrange point is very special for a couple different reasons. Yes, because it's at a stable gravitational location, it's going to take less energy for the James Webb to stay in its orbit. Also, it is such a stable orbit that we can predict what the temperatures are going to be, which allows us to have a more efficient thermal design system compared to the Hubble, which is orbiting around Earth. It's a really, really good place to do space observation.
All right. Let's go check it out. Krystal takes me to the viewing platform for the high bay where the James Webb is being assembled and tested. What do we see here?
Oh my gosh, look at this. So we have such a special privilege to be able to see the mirrors that are actually facing the high bay today. So this is really a treat.
We're looking at a gold mirror, but it's made with 18 different hexagons that are all facing towards this collector, I guess.
So unlike Hubble, which could fit into a rocket in its one solid piece, we have to fold the James Webb up and then deploy it once we're in space.
Amazing. Okay, and then what's this other piece underneath it? This big, it's a huge, it looks kind of like a kite, very silver, 5 different layers.
Yeah, so the second segment we're going to talk about is called the sun shield segment. Now, as you described, it's 5 layers of a capped-on material that's very similar to mylar. It's very thin, but it has properties that allow it to reflect the heat that's going to be coming from the Earth and the sun and keep that away from the optics. So underneath the sun shield is actually our spacecraft. That's where all of the subsystems that make James Webb work. That's where our propulsion system is, our power system is down there, our command and data handling is down there, and all of those elements are important so that we can actually function James Webb.
So that's how you might orient it and move it, point it where you
Yep.
want.
So the propulsion system, small thrusters on board so that we can fix our attitude control, fix our positioning, and orient in the direction that we want to.
And so how long is it going to take to get from here to there?
After we launch, it takes about 15 days to actually make it through all of its deployments. It has to deploy antennas, it has to deploy the solar array, it has to deploy radiators that deflect heat. The entire sun shield has to open up and be tensioned. The mirrors have to unfold. Once we're there, we're going to do about 6 months of commissioning, which is essentially, turning things on, aligning all the mirrors, making sure that everything is working before we get any data back.
And that will be a nail-biting 6 months.
That'll be a nail-biting 15 days will be also a very nail-biting moment.
Yeah, so how long is this going to be out there?
Yeah, so we have a requirement from NASA that the James Webb needs to operate for 5 years. So although we're designing, our requirement is for 5 years, we actually have enough propellant on board that we actually think that the mission will last longer than that, hopefully closer to 10.
Awesome.
One of the cool things to point out here is you can see that there's a lot of folks out there working on the floor, and they're all wearing this white suit. We call it a bunny suit. And this is incredibly important because the last thing that we want is to get any contaminants or dirt or anything on those mirrors and distort our images. So we keep this high bay incredibly clean just to make sure that they don't have anything that falls on the observatory.
Okay, look at those guys walking around. They're like inspecting. What are they doing?
We have different colored hats. When you're in those bunny suits, you can't tell who anybody is, right? Everyone's wearing the exact same thing. So you don't know if somebody's from the quality team doing an inspection, if they're the responsible design engineer, the test conductor, or just a technician. And so one of the things that they had to do was come up with different colored hats that, depending on what your function is, that's what you wear so that you can be able to communicate better when you're in the high bay.
And he's marking things down. You're using paper.
So one of the things to note, you can actually see that it doesn't look like normal notebook. It's actually a blue color. So the paper that we allow in the high bay is special paper so that, again, we don't have any fibers coming off of that. So you can't just print off of a printer and bring any of that in the high bay. It has to be very controlled.
I see squares. There's like a whole row of squares.
All of that yellow structure is something that we call mechanical ground support equipment, or MGSC. When we do a lot of our operations, specifically our deployments, we're operating here in a gravity environment. But in space, it's a zero-G environment. So in order for us to practice our deployments, we have to simulate a zero-G environment. So there's a whole nother effort, in addition to designing the flight hardware, is to design those mechanical ground support aids.
After our tour, Krystal and I meet up with Scott Willoughby, the director of the entire James Webb Space Telescope program. Tell me about what your role is with this whole program.
So big programs like this, NASA is the agency for the United States that really takes on the biggest challenges. And in the public's eye, from moon landings to space shuttles to going to Mars to going past Pluto, that's NASA. And NASA pushes that envelope. And they go to industry. So working for Northrop Grumman, we competed for a program like this. And we won. And Northrop Grumman won the James Webb Space Telescope prime contractor. But even then, it didn't stop there. We have subcontractors and suppliers around the globe that work for us. So we work with NASA. And I am Northrop Grumman's program manager. So when it comes to James Webb Space Telescope, I'm the highest name on that org chart. My job is singular. It's to ensure we build it. We make the requirements, we perform on schedule, we perform on cost, we meet with all what we call the stakeholders, whether it's the public or Congress or, our own executives to make sure we're on track. I'm that person at the top that, tries to ensure we're holding to it. And also, I love moments like this where I can communicate about it.
And the buck stops with you, but you also have the opportunity to share the story.
I've been on the Webb telescope in this job for 9 years, but it's a once-in-a-lifetime mission.
Amazing. And so what's your role?
I actually work on the actuators that initiate all the deployments. So even though there are 178 very small pieces, they make up a large portion about what the James Webb has to do, which is deploy.
It's the special sauce about the James Webb. So who is James Webb? Tell us.
James Webb was an administrator of NASA, and he was a non-engineering administrator. It's actually a great story if you go look back, because every science telescope or something of that nature tends to be named after a scientist. Kepler, Hubble himself, Spitzer, Herschel, Planck. I mean, just go down the line. And with Webb, it's named after, the administrator of NASA, so an agency, but he wasn't an engineer or a scientist. He came about with a business background. He ran the agency. He was there in the 60s, and so he was there from Kennedy through Johnson. And when he was there, it was about going to the moon. And the moon was, to some degree, a race for power, right? To be more powerful than our enemies, let's be blunt, right? So if we can get to the moon, it was another show of force of how powerful we were. And we did it, right? We got to the moon and safely back again. James Webb said, well, if we're doing all this work to get into space, maybe we could do something else when we're up there other than, bringing some moon rock home. So, it's a high ground. When you get out of Earth's atmosphere, you can do amazing things that you can't do from Earth. James Webb was the inspiration for the great observatories that came later, like Hubble or the Chandra X-ray Observatory, the Compton Gamma Ray Observatory. Because of that inspiration, many decades later, they decided to name the next most powerful space telescope after him.
Amazing. And just to hear the story that he's not an engineer. He's kind of an everyday person. We can all aspire to doing that. Yeah. And I want to get back to some of the details about the telescope, but I'd love to hear about your background. What inspired you to do this?
So I'm fairly early in my career. I've been in the industry for about 10 years, but I like to joke that I've been an engineer since I was about 12. That's when my dad first told me that I was an engineer, so I have a pretty lengthy career.
How did he decide that?
Yeah, so when I was in middle school, I did my first science or engineering competition. I built a Rube Goldberg-like device, and it was very important that I beat out the boys so that I could get on to the science team. We went to a state competition, and of course, our design worked flawlessly, but it was also...
Of course.
Yeah.
I like how you say that.
It worked flawlessly. But it also was, pink and pretty and glitter and space stickers all over the place.
And what was it?
It was a Rube Goldberg. So imagine popping a balloon, but you have a lever that pushes a car, that pushes the marble, that turns the wheel, that burns the string, that hits the lever that finally pops the balloon. And it was the first time I'd done any type of engineering ever in my life. And I just became addicted to it that I told my dad once after we won this state competition, I said, Dad, when I grow up, I want to be an engineer. And he goes, well, I think you already are one.
Oh.
So I think we've been engineers about the same time, Scott.
Yes. I'm the older one in the interview here. I've been in this industry for 29 years, and I call myself a reverse engineer. I'm not the smartest of engineers that came to designing the newest thing. I wasn't the kind that came inspired, said I can make something nobody ever made before, and for whatever reasons. And I was kind of intimidated to go on an engineering path. I came from a blue-collar family, but I went into school to become an engineer because I kind of thought if I could succeed at that, I can get a job, as simple as that. But what happened was when I came into industry, I got surrounded immediately by people that were, brilliant in my mind. But I found a niche where people would design things that would go and get produced, and the first test would run and would have a problem. And I would be the person to figure out what went wrong. And I would go back and figure out, was it the test setup? Was it the actual piece of hardware? Whatever it was, I became adept at what I call reverse engineering. I could take a situation, figure out what to do to make it right, and then collaborate with that.
Well, I'd love to talk about that because you hear a lot about embrace failure. And in Silicon Valley especially, it's people always talk about iteration and rapid failure. But you're talking about a $9 billion telescope. How do you iterate and how do you fail on a $9 billion instrument?
You fail on the ground. And it's the simplest statement. We don't have an option to fail. And, we quote the failure is not an option, but we don't in space. When I say that, there's redundancy in the system. If something goes wrong, there are several things that have a backup. You fly 2 of these or 2 of those. But the non-explosive actuators that Krystal's working on, each one has to work. If you put a second one in there, it's like putting one extra hinge in your door. That hinge has to work. It may help it open easier, but from reliability, you made the door less reliable because you just have another moving part and they're all there. So for Webb, it's test on the ground and to test to more extremes than you ever predict it will see as it launches and it gets there. In very simple terms, our design is twice what we actually predict it will be, certainly in terms of a mechanical stress. So we run it in an environment where we shake it twice as hard. Thermally, we tend to put 10 or 15 degrees more on the hot side or 10 or 15 degrees, more or less on the cold side. But in a mechanical, we tend to have to design twice as much, and then we test it for twice as much. And if we don't pass those rigors, we redesign and we test again. Mm-hmm. So when we launch, it's the most benign environment that it will see.
So in sending this out into space, what are the biggest challenges that this particular instrument is seeing that we've never seen before?
So big fun facts again, 16 feet diameter cylinder on the top of the rocket. Telescope deploys 70 feet long by 40 feet wide, which you can use a tennis court in your mind as the size of our sun shield. An optic that's 22 feet across. I told you the top of the rocket's 16, and so we're already bigger. So we had to segment our mirror and build it in pieces and then fold it up and then redeploy it. So that's one extreme, which is the size and then compacting it and then deploying it. We're going to find stars that were really the genesis of the periodic table, and we're going to find the light because that happened at the first stars. But that light was shifted into infrared, and infrared's heat. So if you're looking for very faint photons that are in infrared, but everything else is given off infrared because Earth is, Moon is, right in there, we have to run the telescope cold, minus 400 degrees Fahrenheit, because we have to be colder, which means every piece that's in that cold environment had to be designed to behave. And we know the glue, the composite materials, the metals, the coatings, either something we already knew would behave. We said, well, maybe it could behave better than we thought it ever could. Let's go find it out. And where it didn't, we had to come up with something that wasn't readily available.
So you never really know how long it's going to take and how much it costs.
It is very hard. And with a space telescope like Webb, you're only building the one. So it makes it really hard for the team. It puts a lot of challenge, on them. But you revisit it, we actually revisit in our program meetings every month.
How many people and organizations are involved in this?
Yeah, so people-wise, hundreds. I mean, probably upwards of 1,000 at this point in time between Northrop, NASA, mostly through Goddard, and then the Space Telescope Science Institute. But at one point in time, we had probably well over 100 or hundreds of suppliers. Some of them literally just making some aluminum piece for us. Some of them doing very complicated booms that had to deploy. And that's when we were in production. We were at our high point. So I would say thousands of people were working at any point in time to build a part or verify that part worked or.
Is there any part on there that's off the shelf?
That's a great question because I will say there's a lot of things that as complicated as Webb are, that are not as hard as other satellites. So let me take the power subsystem. Power is hard. We're 1 million miles away from Earth, and we have to catch the solar, the sunlight, and we convert that. But we always have the sun on our solar array, which means we need a very small battery. A satellite that's giving you direct TV that's in what's called geosynchronous orbit, only 22,300 miles away from Earth, periodically goes through eclipse. And the way the satellite behaves is the solar array gets eclipsed, the system switched to the battery, you run the system off of the battery, then the sun comes back out, you charge your battery back up and you go. That's a more complicated system. So in power, we don't have that difficulty. So in that regard, we weren't stretching. We more had to stress the packaging of our solar array. How does it fit? But not necessarily how much power it has. We're probably less than 1/5 the power of a direct TV satellite. We're like maybe 2,000-3,000 kilowatts, and they're probably 15 to 20,000 kilowatts.
Can you name a handful of the things that you've had to invent from scratch?
Probably one of the things is a thing called a spectrograph, that it will allow us to take that light and break it up into its frequencies. And then by, again, I'll call the fingerprint, it'll tell us, it'll confess something about, where it came from. When it does that, the instrument collects the data like a camera would. But what if I can individually turn off the bright object on what I'll call this focal plane array and only focus on it? So in front of it, we have a thing called micro shutters, which at the pixel level, imagine all of that as a little window array. And then I turn off all the shutters where I don't want to look, which means I block their light out. So the faint thing I'm looking at, it's the only thing I'm looking at.
Crazy.
I'm going to see the fainter thing better.
And wow.
And we're going to be able to do that with what's called a micro shutter array. But that's one of the technologies. The coatings on the sun shield, in order to give us this, we have a 600 degree Fahrenheit temperature differential, and it occurs over the span of, a couple feet, and it's by 5 layers of Kapton material, and they're only 1,000th of an inch thick, so that we can fold them. If they were too thick, we wouldn't be able to fold them and make the parachute, stay in there. So we had to cover everything materials with exotic coatings. That's the technology.
One of the other new technologies, the things that we had to invent, is actually aligning the primary mirror. So we talked that, there's 18 segmented mirrors, right? This is the first time we've ever sent a segmented mirror into space, but it has to act as if it is one. You can't see the seams between all the mirrors in your images. That wouldn't be nice. So there's actuators on the back that allow you to align that. Well, they're aligned to 1/10,000th the thickness of a human hair. And that was kind of a new technology that needed to be invented. And even the mirrors themselves, right, is new technology. We don't typically make mirrors out of beryllium. And there was a lot of effort in terms of research and development to, how do we make a lightweight mirror that is strong enough to be able to withstand the temperature differentials. We don't want the mirror to deflect when it's exposed to environments. It has to be very rigid. It has to be very strong. What can we make these things out of? And beryllium ended up being the solution to that. So each one of those mirrors starts out about 600 pounds when they actually manufacture it. And then they hollow out the back, they polish it. By the time it's said and done, they've reduced that from 600 pounds to about 47 pounds.
That's only 47 pounds?
Yeah.
One
it's
segment.
One segment. I mean, it's lighter than my dog. I can probably pick it up.
That's crazy. This is incredibly complex. You have 1,000 people you're working with.
Even a recurring thing in space is complicated. A first of a kind in space is that much harder. A first of a kind in space that is breaking boundaries in size and numbers of deployables and temperature extremes is even that greater.
And it's a million miles away.
Those things, and it is 4 times further than the moon, the furthest humankind has ever been off of our planet.
But to clarify, this is not a manned mission.
It's not. No, but where the reason I was going to use that contrast, people have been or got used to for at least a while that we can go into space and service a mission like Hubble. Even if we had the space shuttle or say the next incarnation of Hubble is only 350 miles away from Earth. Hubble, we're in Los Angeles, is closer to us when it goes overhead than San Francisco. So it was accessible in low Earth orbit. We're going 4 times further than the moon. We are not serviceable. We have to work when we get out there. Like I said, we build in redundancy. We have motors on our mirrors so we can change our prescription on orbit. We've got all kinds of cool things we did to make it what I'll call robust. But it is what we'll have out there. So we need to make sure on the ground everybody says it's good. In the end, sometimes you can't test it. We cannot fully deploy the sun shield in a space-like environment on Earth. Period.
You're listening to The Art of Manufacturing. Follow our adventures on Instagram and Twitter at @ArtofMFG. And to chat with other like-minded creators, join the Art of Manufacturing Facebook group. We'll be right back after this break. I want to give a shout out to DLA Piper, a global law firm with lawyers throughout the U.S. and across the globe, and clients ranging from emerging companies to multinational enterprises. I'm a fan of DLA Piper because their team has been really generous in supporting the Art of Manufacturing, and the Make It in LA initiative is a founding partner. And they've always had someone on their team who's knowledgeable about whatever off-the-wall issue I throw their way. For more information, visit makeitinla.org/DLA Piper. We're speaking with Scott Willoughby and Krystal Puga of the James Webb Space Telescope. You've testified in front of Congress. Was that recently? Or also many times?
Fortunately, I didn't myself testify, but I do communicate with Congress continually. And the most important thing about communicating with Congress continually is throughout the life cycle of the program, not only when there's a problem, to actually show them that, yesterday's problem was solved by the time I come back today, but tomorrow's worry is in front of us and what we're doing about it. And that's a constant flow. What happened behind us, what are we doing now and what's in front of us? So I will meet with them 1, 2, 4 times a year, the committees, with the changes based on the budgeting cycle and that stuff. But if every time you go into your customer, your hand is out, it's palm up and you're looking for something. Those are always tough meetings, as opposed to you go in there some meetings where your hand is out just to shake their hand and say hi and how you're doing and explain what's going on. We have to have both meetings. So we, really make sure we engage with the folks who represent the taxpayers on a continuous basis so they know it's hard.
I'm actually curious why, if that communication happens continuously, why recently there had been a lot of publicity around the increasing costs and time.
When you finally have to increase the program cost at complete, that's the time where you deal, let's say the big elephant in the room. There's a point in time where you got to bring all of the things, and it's hard for the public to understand that. If you have even a 2-hour hearing is talking about a 15-year program and a prior 7-year performance and what's in front of it. So, you get to the point, and those things that dominate the conversation are what they are. But it doesn't mean that it isn't preceded by things. Sometimes the summary level hits what gets hit at the summary level.
Yeah. How long ago did this project start?
So in the glittering eyes of which I never got back to, whose idea was this, which I don't think there's one person. I do hear Dr. John Mather, the Nobel Prize winner, who's our chief for scientists. I don't know if that's the correct terminology, drew a Webb telescope up on a napkin at one point in time, but that's in the 90s. And then in 2000, there's a thing called a decadal survey that said astrophysics was looking for a large infrared telescope. And then in 2002, the formality of the contract started. So the bidding process completed in 2002. And then it was, all right, here you are, go build the James Webb Space Telescope. So very long cycle development, right? From then, there still was a lot of engineering. There was 10 technologies not developed yet, 10 major ones. There's probably 100.
Crazy. Do you think we were spoiled by Apollo? It seems like it almost was an unrealistic, unreasonable expectation that we can actually get to the moon in nine years. And I know this is way more complicated. I'm not comparing, but I just wonder whether...
Yeah, we're spoiled by the result of it being described 50 years later. Because if you were there in the 60s, you would be going through what we're going today. And they were bold, and they were driven by, the President of the United States and by our country using this as, again, a sign of power and superiority, right, technically. But if you really go into it, that journey was incredibly hard. But of course, when you see it at the end, yeah, we were successful. So then we should be able to be successful in everything we say we're able to do. That you can't ever be spoiled by that. You can't say because I said I could do one really hard thing, I can do every hard thing. But likewise, you should never stop challenging yourself to do that next hard thing.
And I'm so happy we are.
Yeah, I mean, if we didn't, I don't want to be the generation that stops.
So I want to talk about the other impacts. to the James Webb, because we talk a lot about why we're doing it from the standpoint of the science and the discovery and looking back in time, but what other impacts, what kind of technologies might come out of this?
So engineering the Webb telescope, sometimes there's even a blur of science and engineering. Scientists are looking for a tool that will help them answer questions. Engineering is designing and developing something. And as you engineer that, invariably, you do two things. One is we're engineering a set of components and systems that will be used for bigger telescopes. So it used to be one single mirror.
You mean we're going to have bigger ones even after this?
We're doing a 6.5 meter telescope, and that's going to find signs of life on exoplanets. And then if we want to look on the surface of that planet, we're going to build a 12 to 15 meter space telescope. With Webb, our surface figure accuracy, the precision of our optics, it's down to the size of bacteria. It's units called nanometers, and we're like 20 nanometers. That's very, very precise. To measure that precision, you can't do that with standard technologies. So we had to come up with some interferometry methods of where you're kind of, the speed of light, how it is, so you know how far it would have went if it bounced off of something and come back, and using all these techniques. Well, people now use that. Ophthalmology uses that to characterize human eyes.
That's happening now based on the technology.
That is already a spin-off technology for Webb. That is one that is out there and being used. But at the beginning of the program, we didn't say, and oh, by the way, when we're done, ophthalmologists, somehow that happened.
Who owns the IP, the intellectual property from these innovations that are coming out of it?
Two flavors. A lot of what we do on contract for NASA direct is owned by NASA and therefore owned by the U.S. and it can get repurposed and spun, and a lot of it is. But there are things that companies, not just Northrop, but our suppliers, that we invest in our money to discriminate ourselves and our performance. And we do that with our own profit. And as long as we invest that and protect that and do that, and then we use it on this program, then we sustain that technology to be our intellectual property. So there's a shared amount of IP. A lot of it is developed on contract, but some of it was developed in-house.
Tell me about your 16-year-old self.
Let's see. When I was 16, I think James Webb had just about started. So
I won't say the same thing.
I told myself one of these days I will work on the James Webb Space Telescope.
Really?
And I didn't think that I would because, it was supposed to launch several years back. But the fact that I was able to accomplish that, looking back now, I'm like, I can't believe I accomplished one of my goals is to work on the James Webb Space Telescope.
What inspired
It wasn't a
you?
direct path, obviously. Yeah. I came to work for Northrop Grumman, and I was working on environmental sensing satellites for several years, and then finally made my way onto this program. I was very inspired by astronomy as a kid. I started the astronomy club at my high school, but I knew very early on that I wanted to build things more. I mean, stars are great, galaxies are great. But to me, I didn't want to analyze that data. Somebody else can analyze that data. But contributing to the engineering that they can then use, they can use a product that I helped work on. That's what I wanted to do.
Where'd you grow up?
I actually grew up in the Central Valley in California. It was very much, kind of cowtown USA.
That's a whole other world.
Lots of cows, lots of corn. I remember the first time I went to my school counselor and told them I wanted to go into aerospace. They kind of looked at me and said, well, we use planes for crop dusting. Is that what you want to do? And I was like, no, that's definitely not what I want to do. So it was a very foreign concept to everyone that I interacted with in high school, and teachers. They had no idea how to guide me to what I wanted to do. So it was very scary, kind of, graduating from high school and moving across the country to go to school and pursue my dreams. So
your dad was encouraging you, though, clearly, with the science project you talked about.
Yeah. So my dad was my earliest fan, my biggest inspiration.
What did he do?
He actually, didn't even graduate from high school. He's a truck driver. He's still a truck driver today, and he obviously didn't have the science or the background to help me from an academic perspective. But I remember he would find coworkers that were engineers and send them over to the house and say, I can't help you, but they can. He would stay up all night with me working on these projects. And so, even though he had no idea what I was doing, he knew that he wanted to support my dreams. So I'm very thankful to have had him.
How about yourself?
I did not have that inspiration. I was going to be a bartender. I was a bad kid at the age of 16. Trying to make it through high school, to be blunt. I was inspired to get a job to pay my own rent and get my own car, and that was as simple as that. And I lived a lot of my time with my grandfather, who was a bartender. And unbeknownst to me then, that influence in helping me communicate with people from all walks of life would come to be one of my more valuable assets, into a career, as I watched him talk to people who either worked at the track and the Meadowlands in East Rutherford, New Jersey, or the lawyers or the accountants, that were in the town. So for me, as a troublemaking kid, I knew I was adept at taking things apart. I grew up on the other side of the Hudson River from Wall Street. I had a negative image of Wall Street in the sense that I just thought there was, greed and a lot of rich people, and I was a poor kid. And being good at math and science seemed agnostic to that. It seemed like there was always an absolute answer. If you add these two things together and you get that answer, and if you could do that better than others, then you were better. So doing well, eventually later in high school, I figured out it was important enough to graduate high school, and a friend of mine put an application in my hand for college, which I wasn't going to apply because I was going to be a bartender, and I filled it out and I got in school.
Where'd you go?
Lehigh University.
Oh, great.
And they gave me enough financial aid to make it worth my time. So I thanked them for that. And then I went in and I became an engineer, and I hired into TRW, which is a company that Northrop acquired in 2002. I've been in the same company for 29 years. But then the only reason I'm here in California is because my brother, after 3 or 4 attempts to go to college, moved to San Diego. I came and visited him in January, and I said, I'm going to come to California. And I wrote a letter, a handwritten letter to every electrical engineer at Lehigh that was working in Southern California, and somebody from TRW responded to one of my letters.
And what would your 16-year-old self say about you now?
It would be shocked. Not only that, all my friends who were my friends at 16 are, more than shocked that I hold a job, that I wear a collared shirt.
What would your 16-year-old self think about you now?
I think she would be very impressed. And in fact, I mentioned my dad was a truck driver. When I was applying for school, I wanted to go to Embry-Riddle Aeronautical University. I'm from California. This school is in Florida. We couldn't even afford a plane ticket to get out there. So my dad convinced his job to give him loads along the way so that he could drive me to college. And we showed up at my university in a 18-wheel diesel truck.
That's awesome.
And everyone was there with their Mercedes-Benz and their BMWs. And I remember my dad just being I don't know what was going through his head. Through my head, I was horrified. Of course, I'm like, oh my gosh, I can't believe.
Can you drop me off a block ahead?
Yeah,
Dad?
block me out. I'll walk the rest of the way. To struggle for so long and, literally have to take an 18-wheeler to get to college because I couldn't afford a plane ticket is incredible to me. I mean, I got kicked out of school twice because I couldn't pay for school. I didn't have enough money for the tuition, but there's no way I was going to get back to California. So I really had no choice. I could keep going to classes or I could stop. And the teachers don't really know whether you've paid your tuition or not, just the financial aid office. So you avoid that office, you go to your classes. And I felt like I bummed meal plans off of my friends. And so they kept me fed and housed for probably about, 6 or 7 months. But I made it out. And so I think my 18-year-old self would be very proud.
You made it. That's amazing. So what's the status now and what's on the horizon?
We're in the thick of our integration and testing phase. All of the hardware has been developed at this point in time. We have a scheduled launch date of 2021. So between now and then, it's all about getting it right and integrating everything together.
It's an amazing phase. 100% of the hardware has been built. It took us 8 years to make the mirrors. They started as beryllium powder in a mine in Utah, right? And then eventually, I always like to declare their last step was to be gold-coated in New Jersey, so we put the bling on it, right? So Jersey going to take credit for that. But we've built all the hardware, and that was a humbling set of years, many years, And then we put this one on a ship. We actually put it on a boat, and we send it through the Panama Canal to French Guiana. We launch on an Ariane rocket, a European Space Agency rocket called the Ariane 5, and send it 1 million miles away from Earth to do its mission.
So that's an unusual place. Do you get more thrust there, or what's the purpose?
Yeah, the reason the launch base is there is because it's close to the equator. And the closer you are to the equator, what you get is more benefit of Earth spinning and throwing you off of it. Most of our satellite launches that go in what's called geosynchronous orbit go from Cape Canaveral, so it's nice to be in Florida. Our version of closer to the equator, French Guiana even closer, coming up from South America. We also launch from Vandenberg, which is really north, but those are called polar satellites, so they have a different orbit.
One of the other things that the team is doing right now is actually learning how to operate the James Webb. So we have, scenarios where we're all in front of a computer. We have the headsets on, similar to old school NASA, and we're practicing, okay, we just separated from the launch vehicle. What's the first thing that happens? Learning how to read that telemetry, learning how to operate so that in case anything goes wrong, we know how to react. And if it goes right, we know what signals we're looking for. So we're going to practice that deployment sequence. We're going to practice us getting it to L2 over and over and over with all the right people in the room to make sure from an operational perspective, we know what to expect.
How can people learn more? Where do they go?
Many places, jwst.nasa.gov, certainly the first. Northrop Grumman, our own websites itself, a movie called Into the Unknown, a publicly available movie, 37 minutes long, created for the purposes of inspiring. And you can get that for free on either YouTube or through our company website.
Thank you so much for allowing us to take a look at it. And I'd love to hear the behind the scenes of what it's taking to make it happen.
Well, I thank you.
We're looking forward to that launch and seeing what happens.
Yeah.
Thank
2021.
you. Thank you. I think the 3 most interesting lessons I learned today were, first, I love seeing the guts of a project that's taken decades of foresight. We don't value long-term thinking in business much anymore. Public companies have to deliver results for shareholders every quarter. And although there's a lot of hype about entrepreneurship driving innovation these days, venture-backed startups are expected to get acquired within 5 years or so. And so it's really hard to pioneer groundbreaking innovation when you're under these kind of time pressures. The James Webb Telescope is an example of what can come from longer-term R&D. Could you work on a project that would take more than a decade? I worked on a project for NASA once. That was almost 30 years ago, and as cool as it was to work on the space shuttle, I have to admit I prefer the faster pace and lower overhead of startup life. It takes discipline to see these science projects through, and so kudos and thanks to those with the patience to do it. Also, I knew the project was complicated, but I had no idea how many ways they're pushing the envelope. 10 totally new technologies, and 300 single points of failure? That's a little nerve-wracking. Not to mention, it can't ever be serviced. So it was interesting to hear about their process for taking risks and iterating. They still do it, but basically, the key is to fail early while the stakes are lower. And finally, it doesn't hurt to have an almost unlimited budget. Well, I mean, it's not truly unlimited, and they're in the news right now for big cost overruns and delays. But you know how they say low cost, quality, and speed. Pick 2. Well, when you're pioneering something totally new and you can't compromise on the specs, it's probably foolish for us to expect we can predict exactly how long it's going to take and how much it will cost. NASA is testifying in front of Congress today to convince them to reauthorize the program because of the cost overruns. I hope they get the appropriation. I did a little research and learned that the $9 billion telescope costs about the same as only one aircraft carrier. It's only about 1/3 the cost of the Itapu Dam in South America. And amortized over 5 years, and they expect it to run for about 10 years, it's only 0.3% of the annual U.S. military budget, which is $600 billion a year. That sort of puts things in a different perspective for me. I mean, can you put a price tag on understanding the origins of our universe and learning about exoplanets? Why aren't we spending more on science and research like this? But that's my personal opinion. It'll be interesting to see where all this talk about a Space Force goes and whether that will drive a lot more R&D. What do you think? Send us an email or message us on social. Time to wrap it up for Season 3 of The Art of Manufacturing. Don't miss what's next. Subscribe to the podcast on your favorite player and sign up for our email list at makeitinla.org/connect. For show notes, visit www.artofmfg.com. Follow our adventures on Instagram and Twitter at artofmfg. And to chat with other like-minded creators, join the Art of Manufacturing Facebook group. Never miss an episode. Subscribe on iTunes or Spotify or your favorite player. And if you like the show, do us a favor and leave us a review. Or send us a message with your thoughts and ideas to feedback@artofmfg.com. This podcast is produced by At Large and Dangerous in collaboration with Make It in LA and other partners. Visit makeitinla.org/connect to sign up for local LA events and news. A big shout out to Peter Brandenburg, the producer and audio engineer. Thanks for listening to The Art of Manufacturing. I'm Z Holly, and remember, don't just make it, make it.